Good evening, everyone. Welcome to the week 9 live interaction session for the course Renewable Energy Engineering, Solar, Wind, and Biomass Energy Systems. So, today we are entering inside the 9th week of this course. Let's begin our live interaction session within the next 5 minutes. Let's just give some time for others to join before we begin our session for today. So let's just start our session for today. Let me present my screen. I hope I'm audible. I hope my screen is visible. Yeah. So good evening everyone. Welcome to the week 9 live interaction session for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy Systems. I am Pratyumnan from the Department of Chemical Engineering, IIT Guwahati. I am the course team member for conducting the live interaction session every week. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati under the NPTEL program. So in the last 3 lectures, if you guys remember, we have traveled way far than what we had known about biomass previously. We initially introduced ourselves to the concept of biomass in the very first week, where we discussed about how biomass is a renewable energy system, how sunlight or the solar energy is used in biomass systems, the different types of biomass that is available to us. We discussed about the different type of feedstocks available to us, which is what gets converted to biomass, and then it gets processed to form different types of fuel. And then we discussed about the characterization of the biomass, the two different types of characterization I hope you guys remember. One was the proximate analysis and another one was the ultimate analysis. So in the proximate analysis, we discussed about the physical characteristics of a biomass system, that is the percentage of fixed carbon present in the system, the percentage of moisture present in the biomass. And when we moved on, and then we moved on towards ultimate analysis, where we discussed more about the elemental composition or the chemical composition of our biomass system. We discussed in depth about this ultimate analysis and the different experimental techniques to determine the percentage of carbon, percentage of hydrogen, percentage of nitrogen and the sulfur present in the sample. If you are able to recollect, for percentage of carbon and hydrogen identification, we burnt the biomass and then passed it through the KOH tube and CaCl2 tube, the anhydrous calcium chloride. And for the percentage of nitrogen, we employed a method called Geldal method. And for percentage of the sulfur, we burned the biomass and then used the product of the biomass with the barium chloride, so that the barium sulfate will get deposited, and from there we can determine the percentage of the sulfur in the biomass sample. Last week we discussed about the conversion of the biomass to biogas, about how much percentage of energy we can retrieve from the biogas using biomass as a source. We discussed about the different type of numerical problems present in the for designing of the biogas digester. So before designing the biogas digester, we also discussed about the production of the biogas, that is when the biomass undergoes the anaerobic digestion process with the help of microorganisms, the biomass is converted to biogas, which is nothing but it's a combination of your methane and carbon dioxide, CH4 and CO2. So we also saw numericals on how much percentage of the methane and carbon dioxide will be present in different types of feedstocks, like protein based, carbohydrate based and fat based feedstock. So here I would just for recollecting purpose, I'll put a quick question so that you can answer very quickly. What are the different stages involved in the biogas? If you remember, the biomass conversion to biogas actually involves for 4 different processes, 4 different stages. So can anybody tell me what are the 4 different stages that is involved when the biomass is getting converted to biogas? Anybody? So if you are able to recollect, then there are actually 4 stages. One stage, the first step is called as the hydrolysis, where your biomass is getting converted to simple organic matters, and then this simple organic matters undergo a process called acidogenesis, where this simple organic matter is converted to higher carbon acids such as butyric acid and propanoic acid. These acids are broken down into simpler acid using the acidogenesis process, which results in the formation of acetic acid, and then it undergoes a methanogenesis process resulting in the generation of the methane. So these are the 4 different steps. I hope you are able to recollect the 4 different steps in the biogas production. And then we went towards the designing of the biogas digester. If you remember about the different variables that we discussed, that is VB, volume of the biogas, volume of the fluid in the digester, volume of the digester, the hydraulic retention time, and then we discussed about the different type of factors that affect your biogas digester yield, how much amount of your biogas will come out of the biogas digester. We discussed, I hope if you are able to recollect, we discussed approximately 8 to 9 different parameters such as temperature, pH, hydraulic retention time, the loading rate of the material, the effect of toxic substance, raw material availability, and then the carbon to nitrogen ratio, the type of organisms that is present. So many different factors we discussed in the previous live interaction session. and we also solved the numerical problems based on that. And due to time constraint, last week we were unable to solve one particular question completely, and I would like to take that up first before we move forward for today's session. So this is that question. Here let us just go or have a recap of what is this question is about, and then let us solve it step by step. So here the question says it's that you have an engine generator, and then that has to be powered using a biogas plant. Okay, so now the total power requirement for your house, or for your house is 2560 watts per day. Now you are supposed to calculate the volume of the digester unit, which has rice husk as its biomass material. They have given the calorific value as 20,000 kilocal per meter cube, or you can since last time we discussed that this value is very high, we take it as 20 kilocal per meter cube. Let me just correct this. And then we have the generator efficiency, engine efficiency values, and then we are given with the value of C, and then we have that for 1 kg of fresh waste you have approximately 10% of the dry biodegradable mass, and it's given that the volume of a fresh waste produces for 1 meter cube or 1 liter of the fresh waste, approximately 0.65 liter of biogas gets generated. Retention time is given as 33 days. So if you are able to recollect, the term retention time actually means is that the amount of time that your biomass is spending inside this biogas digester. What is the time that is required for the digestion of your biomass to yield biogas? That is the definition of retention time, or alternatively it is called as hydraulic retention time. And here it is actually mentioned we have to add equal amount of water to this slurry. So even here, if you see in the important facts about the biogas digester, we have written that for every kg of your wet waste you have equal amount of the water is added to get the slurry. So can anybody tell me why is this condition exists? Like, why are we supposed to add equal amount of water to the biomass waste so that we can get the slurry? Does anybody have any idea on why is this a condition, or why it is specifically mentioned here? What does the role of water actually plays in this digestion process? Does anybody have any idea? So let me just go back to my screen. So yeah, the question is, why are we supposed to add equal amount of water to our slurry that we generate? Like, we mix slurry is nothing but it's a combination of your water and then the biomass waste. So here we add equal amounts of both your biomass waste and the water to obtain the slurry. So the question is, why are we supposed to add equal amount, and why not something like different? So the main reason why are we supposed to add equal amount of the water is to actually maintain the loading rate. So if you remember, if you are able to recollect the concept of loading rate, that what is the meaning is how much amount of the material you are loading inside the digester. So in order to maintain this loading rate, we are supposed to add equal amount of the water to the slurry. So now the question arises is, why do I have to maintain the loading rate? What happens if I just leave the loading rate and I don't maintain it? So if you remember, even in the last live interaction session and even in the video lectures, it is explained clearly that the loading rate is an important parameter and we are supposed to maintain it. The reason why we cannot deviate from that particular ratio is because if you do excess of loading, let's say you're feeding your digester with the quantity of biomass that exceeds its capacity, or that is too much than the optimum value. Then what happens is, once your biomass gets inside the digester, then the microorganisms will start feeding on this biomass waste, and lot of acid accumulation will start happening. Because if you remember, before the methane gas generation, you have the acetic acid, propanoic acid and butyric acid generation. So the microorganisms will keep on generating the acid inside your digester, and this acid accumulation will increase the pH of the system. So once the pH of your system increases, then the microorganisms will die, will not be able to feed on to your biomass system and then convert it into biogas. So the amount of digestion will decrease, and the gas produced, the yield of the biogas that gets produced also will decrease. If you remember, the microorganism can thrive only within the pH range of 6.5 to 7.5. So if lot of material you feed in, then the microorganism will continuously act upon this biomass, and then the acid will keep on getting generated. So lot of acid accumulation will happen, and then the pH will go low. So pH, as the acid gets generated, the pH keeps decreasing, the pH decreases. So then the microorganisms will not be able to sustain that pH, and then they will be killed. So once they get killed, then whatever amount of extra biomass that you are going to feed in will not be digested, and that will decrease your yield. So this is if I load it in excess. Let's say I load it in a lesser rate. Then what happens is, if you load less amount of biomass, then your bacteria will convert all your biomass to biogas, but the amount of biogas that gets produced for a certain amount of biomass will be less. So the yield, or what you call as the C value, the C parameter, that is how much amount of the biogas is produced per kg of the biomass that you feed in, will go low. So even though you have every other facility available to use at the maximum level, if you use it at a level lesser than its optimized or its potential, then that will lead to an uneconomical process, because you are going to generate less biogas for every kg of your biomass waste that you are going to feed into the system. So as such, when we design, our main focus is to increase the amount of biogas that gets generated per kg of the biomass that we feed in. So that will completely reverse the process, and it will be detrimental for us. So this is the reason why we are supposed to maintain the loading rate. So if you remember, the loading rate for your biogas digester system should be maintained between 1 to 4 kg of volatile solids per meter cube per day. So if you remember, last week we discussed this. Let me move towards week 8 slides. Yeah, if you see here, I hope you are able to see here, we kept the loading rate as 1 to 4 kg of volatile solids per meter cube per day. So this is the optimal loading rate. Anything beyond this or deviation from this particular scale will be detrimental for us, and it will decrease the yield of the biogas that we get from the system, making the process not suitable or uneconomical, and a waste of like money on that particular process. So yeah, let's move on to calculation. And then yes, so let's just start solving the problem. So here we have discussed this previously, but let's just discuss once again. So the output power that I want, so the amount of power that is going to be used up for my house is 2560, and then in between your biogas, so biogas is going to feed your system. In between that you have your generator and engine, and then it rotates, and then that how much, with whatever by the rotation of the engine and the generator only we get power supply to our house. So the amount of power that we get to our house is 2560 watts. In case if your generator efficiency and your engine efficiency was 100%, then in that case there would not have been any issue, because whatever the amount of power that you are going to supply from the biomass will be used to power my house. But here unfortunately there is the efficiency is not 100%. We have a cap. So generator efficiency, if you see here, it's only 75 and engine efficiency is only 45%. So whatever amount of energy that you get from the biogas, if you feed it to the generator and the engine, the same amount will not come out of that system to our house, because some amount of the energy will be wasted or lost in the energy as well as the generator. So that's what is written. So output power, that is whatever the power that we require to power our requirement, is nothing but the input power that we get from biomass times the efficiency of the two system, the generator efficiency and the efficiency of your engine. So the equation is input into 0.75 into 0.45 is equal to the output power, that is 2560 watts. So what is my input power? That will be 2560 divided by 0.75 times 0.45. So if you calculate, last time when we calculated, the input power was approximately 7585.1851 watts. So this much amount of the power has to be supplied from, I have to get from my biomass, so that I will be able to power my own requirement. If anything less, then it will not be helpful for me. So that's what we wrote. Biogas has to supply 7585.1851 watts power to my generator. So this much amount of power has to be generated. So how much amount of the biogas will I require to generate this much amount of the power? So that is our next question. We do not know what quantity of the biogas we require. That we are supposed to find out. We know our energy requirement should be 7585.1851 watts. So then we can write this as, we know what is the calorific value of our biomass, that is 2000 calorie per meter cube. That times your biogas volume will give you nothing, what it gives us is the input power. So your biogas volume times your calorific value will give us the input power. So input power that we are supposed to supply is 7585.1851 watts, and we know the calorific value as 20 kilocal or 20,000 calorie per meter cube. So since it's in calorie and it is in watts, so the unit for watt is 1 watt is same as 1 joule per second. I hope everybody is able to recollect this units and dimension. 1 watt is 1 joules per second. So here, since it is in calorie, we are supposed to convert it into joules. So 1 calorie is 4.81 joules. I'll write this here. 1 calorie is equal to 4.18 joules. So that is the reason this 4.18 factor has been multiplied. So if you divide this 7585.1851 divided by this 20,000 calories times 4.18, how much the volume you are going to get? Last time we calculated as 0.0907 meter cube per second. So this is the biogas volume that is going to be generated per second. Now, so if this is for 1 second, for 1 day, how much are we going to get? For 1 day, how much I get, how much biogas will be generated. That is our question. So let me just this. So for 1 second I am getting 0.0907 meter cube biogas. One day what will be my requirement, how much amount of biogas will get generated. So one day is nothing but, can you tell me how many seconds are there in one day? So this many seconds. So if I am not, let us just calculate this. 24 times 3600 should be 86400. These many seconds. So the total amount of biogas that will get generated for one day will be, total volume of biogas that will get generated in one day will be 0.0907 times 86,400. So that will be 7,836.48 meter cube, right? I hope till this point nobody has any doubt. If in case if you have doubt, then please let me know. So this much amount of this thing, biogas will get generated in one day. So I hope till this point it is clear. If you have any doubts, then do let me know, or otherwise we can proceed for the next step. Okay, so let's just proceed for the further steps. So here we know how much is the amount of biogas that is going to get generated, right? Like the volume of the biogas that is going to get generated in one day. So if this is the amount of biogas that gets generated, how much amount of the parent material, that is the biomass material, am I supposed to feed into my system? Because till now I don't know. What has been given to me is the power requirement that I require for my own system. So from there we and then they told that the entire system of yours is going to be powered by the biomass. They gave our efficiency, so we were able to calculate how much amount of the power should my biogas is supposed to generate. So I calculated that power. Now this is the amount of power that has to be generated. So how much amount of the biogas should be generated to power to supply this much amount of power, and that also we calculated using this input power is nothing but biogas volume, and the volume of your biogas times its calorific value. Now we know what is the volume of biogas that will be generated. I am supposed to calculate so I know the volume of the biogas that is supposed to get generated. So if this is the amount of biogas that I am supposed to generate, then how much is the amount of parent material or the biomass material I am supposed to feed in? Because that is what I will be like knowing, right? At the end, like I will be the one who will be feeding the biomass into the biodigester, and then that will get converted to gas. That gas will be taken up for your power generating application. So the one thing that I can control from my side will be the amount of biomass. So I am supposed to calculate that, because biogas is generated from your biomass. So let's calculate, for this much amount of biogas to be generated, how much amount of the biomass I am supposed to feed into the system. So for that we will use the value C. If you remember what is the C value, like the parameter C, It is nothing but how much amount of the biogas is generated for 1 kg of the dry biomass waste I am going to feed into my system. So that is given as 5.67. Like for every kg of biomass that I am feeding into the biogas digester, I am able to get 5.6 meter cube of biogas for 1 kg of dry biomass. So for 1 kg of dry biomass, I am able to get 5.67 meter cube of biogas. I have 7836.48 meter of biogas to be generated. So for this much amount of biogas, what will be the amount of biomass that I am supposed to feed into the system? Can you just calculate and let me know? The calculation is very simple. You are just supposed to do the division here. So 7836.48 divided by 5.67, that will be 1382.0952 kg of dry matter waste is required. So your value of x will be 1382.0952. This much kg of biomass waste, dry biomass waste, I should supply, like should be supplied by me, or I should supply per day. I hope I am clear till here. If you have any doubts, then please unmute your mic or let me know. So this is the amount of dry biomass waste that I have to supply. But here, unfortunately, whatever I have with me is nothing but is a fresh waste. I don't have a dry waste with me. I have a fresh waste with me. So if this is the amount of dry biomass I am supposed to feed it to my system, then how much amount of dry wet biomass waste should I supply into my system? And that ratio is given. So for 1 kg of fresh waste that you are generating, for every kg of your fresh waste, 10% of it is the dry biodegradable mass. So which means the amount of fresh waste will be this value divided by 0.1, because 10% of something is going to be 138.2, right? So that divided by 0.1 will be your fresh waste. So let me just write 10% of fresh waste is nothing but it is my dry waste. So what will be the, so I know my dry waste now here. My dry waste I need is 1382.0952 kg of biomass, so that I will be able to generate a volume of 7836.48 meter cube of biogas, which will be able to generate a power of approximately 7585.1851 watts. So this is the wet waste that I require will be let me just write mathematically also. 10 by 100 times x is 1382.0952. So my x value will be nothing but this whole divided by 0.1. So that will be 13,820.952 kg of wet waste per day. So this much amount of the wet waste is actually required per day for generating 1382 point this much kg of biomass, dry biomass, that will generate a biogas volume of 7836 to supply a power of 7585 watts, and that will be supplied to my generator to generate a power of to supply me with a power of 2560 watts. So this will be the amount of wet waste. But what are we supposed to calculate here? We are supposed to calculate the volume of the digester unit. Oh, sorry. Now there is again another one term that is given. So for every kg of my fresh waste, for every 1 kg of my fresh waste, I am generating, it is able to generate up to 0.65 liters of biogas, right? So this is for every kg of my fresh waste. Now I have totally 13,820.952 kg of fresh waste with me. So how much biogas will get generated? Because this will be required for our calculation of the digester unit. So if you, it's again just cross multiplying, it's just that 1 kg is giving this much, so this much, so much amount of kg will give how much amount of biogas. So 13,820.952 times 0.65 liters. Let's calculate this also. 13820.952 times 0.65. This much amount of liter of biogas will be generated. Now as we said, we are supposed to add equal volume of the water to this to the system, so that we are able to maintain the rate, right? If you see here, we are supposed to add equal amount of water to the slurry, so that will be so just a minute. I'll just calculate here in my personal. If you got the value, then do let me know. So we are just supposed to multiply 8938 times 2, 17876 point, if I am not wrong, 336 liters. Now this is everything we have done is for per day, but our retention time we know is for 33 days, right? So we are supposed to multiply this with 33. So what will be the answer? So 17876.336 times 33. This much amount of liters will be there, we will get. So let me just oh, so these many liters, and then this you can convert as meter cube, like 1 meter cube is 1000 liters. So if you divide by 1000, you will get this much. This is your volume of the digester unit. So we got to know how to calculate the volume of the digester unit. So first we take our power requirement. This is a kind of, you can say, a back calculation question, or you can also say we have done reverse engineering. So we are given only with the power that is required for my system, like for powering my, let's say, my house or any kind of appliances, and then I am told that only the biogas can do this, and then they have also said how the biogas is going to supply my power after moving through the engine and generator, which has certain percentage of efficiency. After that it is going to come back to me. Now I know my output power, so I can calculate my input power, because that, and we have assumed that there is no loss apart from this loss in the generator and the engine. So with this we can calculate the input power that is supplied by my biogas. So from there I will be able to calculate what is the power that is supplied by my biogas. From there you can calculate the volume of the biogas that is required to supply this much amount of power. If this much amount of volume of biogas is required, how much amount of biomass am I supposed to feed into my system, the dry biomass waste. If this is the amount of dry biomass waste that I am supposed to feed into my system, then what will be the fresh waste that I am supposed to feed into my system? This much will be the kg of wet waste per day. And then after that, once you get to know this, then you will be able to calculate the volume of the digester. Like, you just need to multiply that with the retention time. You will be able to calculate what is the volume of your digester unit. That is nothing but the amount of volume of biogas that will be produced by your system. Now here we move on towards another two questions before we move forward for our discussion today, for our today's discussion. So I hope you will be able to solve the sixth question. It's a very simple question. You just need to estimate the net energy of a biogas which is burned in a boiler. It has a efficiency 70%. The heat of combustion is given as 14. Your volume of biogas is given as 8, and they have given the given data is for every 5 meter cube, for every 10 meter cube of biogas, you have 5 meter cube of methane that gets generated. So you are supposed to calculate the net energy that will be generated by this biomass. So this is very similar to what we did previously in the last live interaction session. So I hope you will be able to solve this. I'll just give you, let's say, 3 or 5 minutes, and then I expect you guys to answer to this question. What will be the answer among the 4 options? You are given with all the parameters that is there in that formula. Yes, what will be the answer? You know the heat of combustion per unit volume of the methane, you know the volume of the biogas, you know the boiler efficiency, as well as you know what is the value of your fraction of methane in the biogas. So, so what formula you will you be using? Yes, I mean this is a very, it's just a straightforward question, and okay, let me just show the formula here. Yeah, you will be using the equation number 2. I hope you are able to see my slide. Let me just zoom in. You will be able to you'll be using the equation number 2 here. Yes. Okay, you can say me what is the value of eta, VB, QM, and FM. I'll just type that here also. E or P, whatever you can take, net energy, or it should be net power, eta times VB times your heat of combustion Qm of methane times your Fm. So eta is nothing but 70% or 0.7. So eta is 0.7, and we know our heat of combustion Qm value as 14 megajoules per meter cube. Volume of the biogas VB is also given as 8 meter cube. Now we are just suppose they are asking us to, you are supposed to know what is the value of Fm. Once you know it, just multiplying. So what is the value of Fm? What do you actually mean by Fm? Because this question is very similar to the one that you would have solved for your assignment problems also. So what is Fm? Like what is the meaning of Fm? Then we will be able to calculate from this question. So Fm is nothing but it is your, I'll say what is it, so you can then let me know the value for it. So Fm is nothing but the fraction of the methane that is present in your biogas. So if you remember, whatever the biogas term actually means it has both your methane as well as carbon dioxide. So every biogas that is going to get generated will have a certain percentage of that as methane, and the rest will be the carbon dioxide. So Fm is nothing but the fraction of the methane that is going to be present in the biogas. You are just supposed to calculate that fraction of methane. It is there in your given data also. So fraction of methane is means how much methane is going to be present in my biogas. So okay, let me just answer it here. So given data says that for every 10 meter cube of biogas that I have, 5 meter cube will be methane. So the amount of methane that will be present is 5, and then this will be present in, and then the total volume of the biogas is 10. So fraction of methane is nothing but volume of the biogas divided by the volume of the methane to that of the total volume of biogas. So 5 meter cube is my methane, the total volume of my biogas is 10, so 5 by 10, that is nothing but 0.5. So it's just now again multiplication, so please tell me, like, let me know the answer, because it's just that you need to multiply, and here they have not asked even to the units are also the same, the megajoules. So if you calculate, then it would be 0.7 will be your burner efficiency, QM will be 14, VB will be 8, and your FM will be 0.5. So 39.2 megajoules. So this is the answer. So this is a very similar question of what you would have solved for your week 8 assignment question. We have solved this previously also in our week 8 live interaction session, if you remember. Here, compared to that one, this one was a very straightforward question. So next we move on to this. Also it's one of your questions in the assignment. What should be the optimum CN ratio for your biogas digestion process? If you remember in the last week session also, as well as today in the introduction of the live interaction session, we discussed about the different factors that usually affect your biogas yield from the when it comes out from like biogas yield in the biodigester system. So one of the factors that affect your biogas yield is nothing but is your carbon to nitrogen ratio. So what should be its optimum value, so that you can get maximum microbiological activity? And the question also we have put forth here is that if there is any deviation in this ratio, let's say I am not going to maintain, I am going to maintain my own particular ratio, then what will be the implications or consequences of that? We are supposed to explain that as well. So what is the answer? This is a straightforward question. So let me give you the answer first, because that is just the optimum ratio value that you are supposed to know. But what we mainly want to know is why this is the optimum ratio and what happens if I deviate from this. So the optimum carbon to nitrogen ratio is 25 to 30 parts of carbon for every part of nitrogen. Now the question is, why am I supposed to maintain like what will happen if there is any deviation from this ratio? Like what will happen if I keep, let's say if this is the optimum one, let's say I am going to keep it around, like reverse the ratio entirely, like for every one part of carbon I am going to have 25 or 30 parts of nitrogen. What will happen if I keep that ratio? Or what will happen instead of keeping only 25 or 30 parts of carbon for every part of nitrogen, what will happen if I keep, let's say 50 or 60 parts of carbon for every part of nitrogen? What will be the consequences of that? So if anybody knows, then please unmute yourself and let me know this answer. We discussed this also in our last week live interaction session on what could be the consequence of going out of the optimum ratio zone. Yes, anybody has any idea on why this should be your maximum microbiological activity? So if you see your biogas digestion process from the biomass parent material is usually happens because of the anaerobic bacteria, and then this anaerobic bacteria usually feed upon the carbon based nutrients. So in order for their survival they require carbon based nutrients. Only if they survive they will be able to feed onto the only if they survive they will be able to convert your biomass into biogas. So for that they require nutrients, and that nutrients is supposed to be the carbon based nutrients. So that is the reason your ratio of the carbon to the nitrogen should be around 25 or 30 times 1, so that the maximum at this particular ratio the amount of digestion is maximum microbiological activity is happening. So let's say I'm going to, as I said previously, I'm going to vary my ratio. I'm not going to keep this 25 and 30, or I don't know this ratio. Let's say I'm not aware that I'm supposed to keep this as my ratio, and then I just try an experiment. I just play with these numbers, play with the carbon parts as well as the nitrogen parts, and then see what is going to happen inside my system. So if I do that, let's say I'm going to keep for the ratio as 1 is to 25 or 30, or for every one part of carbon I'm going to have 25 to 30 parts of nitrogen. Then in that case, if you see for the option C, nitrogen is more, right? So if nitrogen is more compared to carbon, then what happens is that the anaerobic bacteria that is present in your biomass or that is present in the biodigester will feed upon the carbon first, and since it's only very limited in amount, they will consume all of them, and then the excess what will be present will be only the nitrogen in the biomass. So what happens is, in that case there are chances that this nitrogen whatever that excess is present will react with the hydrogen present in your biomass sample. Yeah, hydrogen will be almost already present in your biomass sample, right? So there are chances that this excess of nitrogen and then the hydrogen, those two compounds will combine together, will react together as if you remember the reaction is N2 plus 1.5 times of H2O will give you ammonia. Like if you react it in that way, if both of them starts reacting, then ammonia generation can happen. That is nothing but is a NH3. So N2 and then 1.5 parts of, or 1.5 times of hydrogen gas. If both the gas react with each other, then it might result in the formation of your ammonia, and then this ammonia concentration will keep on, if it keeps on increasing, it will be toxic to your bacteria, and your bacteria will die. So if your bacteria dies, then as we said even previously in the loading case, why what will happen if our bacteria is dying? Bacteria is the one that converts our biomass to biogas. If that itself is going to die, then there will be no digestion. If digestion is not happening, then ultimately the biogas product will not be formed, so that will make the process uneconomical. Okay, this is fine. If I'm having a lot of nitrogen, then ammonia is going to get formed, and then my digestion process is going to get completely stopped. Possibilities are there. What happen if I keep very high percentage of the carbon? Then also what happens is similar. Over there, let's say if I keep 50 to 60 parts of carbon for every part of nitrogen. So the bacteria will come, it will consume up all the nitrogen, and then the excess of the carbon will be present in a lot of quantity. So that will also slow down my digestion process. So either way, when I do this experiment, I will be in a place which will be uneconomical to me. So that is the reason why we are supposed that so that is the reason why this will be the optimum ratio. I hope you are able to get it. If the nitrogen content is more, ammonia can form. If carbon percentage is more, then also your digestion process might slow down. So that is the reason the optimum carbon to nitrogen ratio has to be maintained in your system. So whenever anything is written as an optimum, then I guess it would be best for us to understand what happens if we actually deviate from that optimum ratio and really know what will be the implication of that. It's better to have an understanding of that so that we can prevent ourselves from making mistakes in the process, so that time will be conserved, money will be conserved. So that is the reason every single process that we have, usually they use the word optimum, so that we do not so that this will be the optimized system, and this will be, if you maintain this, you will be getting what do you say, benefits out of that process. If you vary the ratio, then it might not be beneficial for you and it might be detrimental for you. So that's how we even discuss, if you see all the 5 factors or 6 factors, what happens if I vary my loading rate, what happens if I vary my pH, what happens if I vary my carbon to nitrogen ratio. So I hope you have got a clarity now. In case if you have any doubts, then please let me know now, because we are going to move forward to our week 9 content, like the biomass conversion into different type of products. So if you have any doubt, then let me know now. So in the week 9 we will be again focusing on biomass conversion. So here we will be discussing every single process in detail of pyrolysis, gasification, combustion, and then in the ethanol we will be discussing about the ethanol fermentation. We won't be discussing about this anaerobic digestion process, because we discussed this concept rigorously in depth in the last week session and the week before that also. So here we will be discussing only about this thermal conversion as pyrolysis, gasification, combustion, and then we have one more process called torrefaction, and then in chemical conversion we will be moving for ethanol fermentation. So if there are no doubts, then I guess we can move to the biomass conversion, the topic for week 9. So as such, if you see this slide was actually adapted from the slide number, was actually adapted from the week 7 live interaction slide. So if you see, both the slides are actually the same. So here the chemical conversion, here what we have is the first is the ethanol fermentation. So you are supposed to ferment your ethanol, and where do we get this ethanol from? We get the ethanol from so first one is your ethanol fermentation. So that you usually get it from your glucose, and that glucose is nothing but it's a simpler product of your higher content like sucrose or the C6H10O5 times N, the higher complex sugars. So here you will be getting the ethanol, and if you remember in the video lectures, Professor Vaibhav Vishant Gaut sir has explained in detail about the different ways of generating the ethanol, the process flow sheets. So we will not be discussing that here. So if you go to your video lecture, you will be able to see the, I hope you have went through, or if you haven't, then if you go through that, you will be able to see different type of flow charts for the production of the ethanol from the different type of feedstocks. Like one will be the edible feedstock and cellulosic feedstock, what would be the differences in the process that will be happening, and what are the different various processes that are there present in ethanol. Like if you see, it will be extraction. First you will be extracting the juice out of your sugar cane. So if you take sugar cane as your parent material to derive ethanol or bioethanol from it, then you will be taking the sugar cane, then you will be extracting the sugar juice, and then you will be doing the fermentation, where so after the fermentation is done, you will be doing the distillation in order to get your ethanol product. So this will be the sequence. You take your sugar cane, you extract the juice from that sugar cane, and then you ferment that, and then you do distillation in order to get your ethanol. So this is about the chemical conversions that is involved in the process. Coming to the thermal conversion over there, so as such, if you see biomass conversion, the biomass itself can be used as a material to generate heat, or it can be converted to useful chemicals like ethanol, bioethanol, biobutanol, and then that can be used for various other purpose. So chemical conversion is about that one, where you convert your biomass to other useful fuels, and then that will be used for your other applications. Let me write this. Convert biomass to other useful fuels. That is about with the chemical conversions. And we will derive energy from those biofuels that gets generated. But in case of a thermal conversion, it's a kind of more of a direct use of biomass. Here biomass is burnt and then the energy is released, and then energy is released from that process. This is about the thermal conversion. So you can say that as I said, the thermal conversion is something more of a direct process, and your chemical conversion is something more of an indirect process of converting the biomass to some other useful biofuels and then using them for some applications. Here whatever the energy that you will be getting, that will be directly used for your application purposes. So what are the different kind of thermal conversions that you can see? Just a second. So here we have, one is the pyrolysis, gasification and combustion. So even in the week 7 live interaction session we saw, we are supposed to know what is the difference between, see, all the three will actually generate heat at the end, will actually generate heat, energy in the form of heat at the end of the process, right? But what is the difference between these three processes? Because what I'm going to take a material subject to these three different processes, what I'm going to, the tangible what I'm going to get at the end is nothing but is the energy, heat energy. But what is the difference in this process? How am I going to get that heat energy from these three different processes? What I am supposed to understand here. In case of your pyrolysis, what happens is you just burn the biomass, but so thermal conversion is nothing but burning of the biomass. But pyrolysis process, here our biomass is actually burnt in the absence of oxygen. You just take your biomass and then put it in a vacuum, and then you are going to heat it to high temperatures. it will burn and then the heat energy will be released. That process is pyrolysis. The next one is the gasification. In gasification, we will be using oxygen. So here we will be doing a kind of burning process with the oxygen, but then that burning will be with the limited supply of oxygen. So there will not be a kind of complete combustion. It will be just towards a limited combustion. So you only supply a very limited amount of oxygen for the burning process. That process is called gasification. Combustion is nothing but either you supply stoichiometric quantity of oxygen or excess of oxygen or excess of air for the burning of the material. We will understand what do you actually mean by stoichiometric quantity of oxygen, but that will we will see that in the next slides. So so the process difference, the differences in all these processes is the absence or the excess or the limited use of the oxygen or the air to your system. That's what differentiates these processes. And then of course depending upon the changes in the processing condition that you are going to subject your biomass, the products that you will get out of that system will be different. Like in case if you see for your pyrolysis, it will be a charcoal, oil, gas, etc. In case of the gasification, if you take, it will be mostly the fuel gas, and then if you in case of the combustion process, you will be mostly getting the CO2 H2O products, hot combustion products. That's what we mean. So this is the difference, and you are supposed to remember the difference. Like if in case if this question like comes up at any time, even after you finish this course, like what is actually the difference between these three different kind of processes that I'm subjecting the material the biomass to. So you should be able to answer that. Pyrolysis, no oxygen, it's just heating of the biomass. Gasification, you do with the limited supply of oxygen. And combustion, you either do it with stoichiometric quantity or excess of oxygen for the complete combustion of your biomass substance. So this you are supposed to understand. Pyrolysis, no air or no oxygen. Gasification, limited supply of oxygen or air. Combustion, stoichiometric or excess, you can say excess quantity of air or oxygen. So now we move to the combustion. Let me just put this in PowerPoint mode. Combustion of biomass. So what is the meaning of combustion? As we said previously, over there we will be using stoichiometric quantity or excess quantity of air for the complete combustion of the biomass. I hope my slide is visible to everybody, because usually when I do this, then at that time the slide may not be visible to you guys. So please let me know whether the slide is visible to everybody. Is my slide visible? Is my slide visible? Okay, so what is actually the meaning of combustion of the biomass? So as we said, it is either burning of your biomass sample in stoichiometric quantity or excess quantity of air. So what is the meaning? Like if you see this word, the stoichiometric quantity of air, what do they mean when they say a stoichiometric quantity of air? So if you see for a combustion process or for burning process, there are totally three things actually required. So if you see in combustion, if you are going to burn a material, combust a material, then you are going to require three things. One is nothing but is your air, because without oxygen supply you cannot ignite the material, you cannot burn the material. Then you require fuel, and then the third one is the temperature. Without these three things, any material will not burn. So enough supply of oxygen, enough supply of fuel, and enough temperature should be there for burning a particular material. So the stoichiometric quantity of air is nothing but, it's also called, if you see, the alternate term for stoichiometric quantity will be theoretical quantity of air. So the definition, or like the exact meaning of the stoichiometric quantity of air is nothing but the theoretical amount of the oxygen that is required to complete the combustion process. So I hope you are able to understand why I am stressing the word complete combustion. All the material should be converted to the products. Complete combustion should happen. It's not that only a partial material has been burnt, or only a particular fraction has been burnt to its products. Complete combustion should happen. The amount of air or the amount of oxygen that is required for complete combustion of the biomass is called as the stoichiometric quantity of the air required for this process. And so usually for the complete combustion, even if we keep the stoichiometric air, it's always better, if you say, to be more specific, to say that for a complete combustion it's always better that we keep stoichiometry only, but a slight excess of that stoichiometric quantity, because so that we can be sure. Usually we do that to make sure that our processes completely get combusted, because sometimes if we give only supply exact amount of air, then the process, sometimes due to some other kind of disturbances in the system, we may not be able to get a complete combustion. So it's always safer to have a certain fraction, not much, a certain percentage or quantity of the air in excess to what is called as the in excess to the stoichiometric quantity. So usually this reaction, if you see, it happens at a temperature between 700 degrees Celsius to 1400 degrees Celsius, and then the pressure over here is supposed to be maintained greater than or equal to 0.1 megapascal. So that is the reaction condition for combustion. If you see in the video lecture, then you will be able to get the idea for what should be the temperature for other processes that is involved, that is your pyrolysis, combustion, gasification, etc. But in case of combustion, this should be the condition. So then we come here to the air fuel ratio. As I said, for every burning process of, for any burning process and for burning of the biomass, three things should be very important. First one is the air, second one is the fuel, and then the third one is your temperature. So without these three processes, your ignition of a particular material of the biomass or any other material will not start. So there has to be a certain fraction or a certain ratio, and that ratio is usually calculated as it is, as you can see from here. So what is this air fuel ratio is nothing but is the amount of air and the fuel that is going to take part in the combustion process, and that is given as, so A is nothing but is your air, and F is nothing but it is your fuel, and the subscript actually means the stoichiometric quantity is nothing but the mass of the air to the mass of the fuel. Amount, as I said, it should be in mass, like here we take it in mass, so mass of air by mass of fuel, and then that can be represented as 4.76 times of molecular weight of air to the molecular weight of the fuel that we take. So this is the air fuel ratio. How much amount of air and the fuel that I require, or what should be the ratio that I am supposed to maintain apart from the temperature, so that the combustion process happens. Next comes is the term is the equivalence ratio. What is the equivalence ratio definition is that the air to fuel ratio, the stoichiometric ratio to that of the air fuel actual ratio, like what you are going to supply in actual and what is the theoretical quantity, that is the what you know, the ratio between those two. So here also you can actually represent it in this previous format. So here if you see, uh, it will be nothing but like mass of air by mass of fuel in stoichiometric ratios to that of the mass of air to the fuel in the actual ratio. And then you can use this next equation, that is 4.76 times mass molecular weight of air by molecular weight of the fuel, and then you will be able to calculate the equivalence ratio as well. So if your equivalence ratio is greater than 1, then it means that the mixture that is you are having is a fuel rich mixture. I hope you will be able to get to know why, because this equivalence ratio can actually be written as F by A of actual divided by F by A of stoichiometric. I will write this. So this can be alternatively written as so this can be written. It's just that I'm inverting the A and F, that amount of air and then the amount of fuel. If you write it in the other way around, then this will be the equivalence ratio formula. So from this you can say that if your phi is greater than 1, then F by A will be greater than 1. So which means that the amount of fuel that you will be putting into your system will be greater than the amount of air that will be present. In case of your fuel lean mixtures, so if there is a word term called lean, which means what it actually means is it is less in amount. So over there in that case, the amount of fuel that is fuel lean, so in that case the amount of fuel that is present compared to air will be less. So fuel will be less than air if the value of phi is less than 1. If phi is equal to 1, that means the amount of fuel that you take and then the air that you are going to take in the actual condition will be the same. So that's what is the meaning of this. Now we move on to the process called torrefaction of biomass. So this is nothing but it is again a before this we have to actually discuss about this classification of solid fuels. So if you see, it's also called as the Van Crevelen diagram. It's nothing but it is a plot between your hydrogen to carbon ratio to that of your oxygen to carbon ratio. So it usually represents for the elemental changes, elemental composition changes that happens when it undergoes this dehydration, decarboxylation and demethylation process. The fuels that has this high oxygen to carbon ratio, that is when you go beyond this 0.81 in the right hand side of the axis, then in that case the heating value, I hope you will be able to recollect what is actually meant by the heating value. That value will go less, it will decrease. And one more thing that you have to make sure here is, the higher the oxygen and the hydrogen content, so this hydrogen and the oxygen can actually react and form water, right? So high volatile as well as the high volatile liquid yield will be more. So you have to make sure that when you select a particular material for the combustion or any kind of the gasification process, then that oxygen to carbon ratio should be low, so that heating value will be more, as well as the hydrogen and the oxygen ratio should also be less, so that your water, that volatile liquids cannot be formed. So this will help, this is a kind of a chart which will help, or graph which will help in selecting your biomaterial for each purpose, yeah, for your thermal conversion purpose to be specific. So you need to maintain low oxygen to carbon ratio so that your heating value will be high, and then the oxygen as well as the hydrogen should be, if it is present in high, then it will actually generate the volatile liquid, so that also has to be low. So these two things you should keep in mind while selecting your biomass for the, or when subjecting your biomass to a particular process. Next we move on to the torrefaction of biomass. So if you have doubts related to the combustion process, then you are welcome to ask me before we move forward to this thermal conversion process called torrefaction of biomass. So this process, what actually it means is, it's again a thermal conversion process, just like in case of your pyrolysis, gasification and combustion, and this also occurs in an inert or low oxygen environment, similar to what we actually saw in pyrolysis and gasification process, but it's different from your carbonization and other gasification process also, even though their processing conditions are similar. So the amount of the solid or the carbon rich solid product that you will get through this torrefaction process will be higher compared to the carbonization and the pyrolysis process, and also other advantages and disadvantages are listed in your video the video lectures. So if you see, you will be able to get a lot of differences between these three processes, but the one of the main differences is that the type of fuel that is going to get generated, or the type of product that is going to get generated. In case of the torrefaction process, it's a carbon rich solid product, but in case of carbonization and the pyrolysis, there are liquid products that will get generated. So in case of torrefaction, then the maximum amount of carbon rich solid products will be generated during this process, unlike in case of your carbonization or pyrolysis. And for the rest of the differences between the process, you are welcome to go through the video lecture. So what is this torrefaction process is all about? So here it's, so if you see the mechanism of the process, it's quite simple. You are going to take your biomass, and then you are going to heat the biomass at a temperature range of 200 to 300 degrees Celsius, and then once you reach to that temperature, you are going to leave it for a set amount of time. So it will keep on getting subjected to that particular temperature for a certain period of time. In this case, when you leave it for a certain period of time, complete hemicellulose decomposition happens here, and that actually helps in maximizing your carbon rich solid products, and energy production will also be maximized. So this torrefaction process is actually classified into three different types. One is that it is so the classification basis is nothing but it's your temperature and then the time of this biomass being subjected to this torrefaction process of raising its temperature and then leaving it at that particular temperature for a certain period of time into three different classes. Classification is based on temperature and then the time that the biomass is subjected to the torrefaction process. It is classified as three types: light torrefaction, medium torrefaction and severe torrefaction. What is the difference between all the three? It's the temperature range. So in case of your light torrefaction, the temperature range is maintained between 200 to 240 degrees Celsius. So in this case, all the hemicellulose will get degraded. So if you take a particular biomass, you will be having majoritively 4 different components. So if you are able to recollect, that is nothing but cellulose, hemicellulose, lignin and pectin. So these are the 4 different components, and in this light torrefaction process, the entire amount of hemicellulose will get degraded, but your lignin and cellulose content will not be subjected to any kind of degradation in this light torrefaction process. But when you move to the medium torrefaction or medium torrefaction, moving from light to medium torrefaction process means you actually vary the temperature. In case of light, you maintain between 200 to 240. In case of medium, you maintain between 240 to 260. In that case, what happens is that the cellulose components also starts degrading. So in the light, it is only your hemicellulose that is going to get degraded, but in the medium case, as you increase the temperature, your cellulose component will also get degraded, and then the products that you will get after, like once you retrieve out of this medium torrefaction process, is nothing but it will be your ash, char, modified sugar products will be obtained through this process. Then you go to the severe torrefaction process. Over there again the temperature range is quite high. Here it is between 260 to 300 degrees Celsius. Here all the three components, whatever is present in your biomass, will get degraded. Both all your lignin, cellulose, hemicellulose will get degraded, and they will be converted to gas like hydrogen, carbon monoxide, methane and other kind of the gaseous products. So in case of a severe torrefaction process, entire degradation happens. Medium, the hemicellulose and cellulose degradation happens. In light, only hemicellulose degradation happens. So this is the different type of torrefaction process that we have. Now let's start solving some problems related to the combustion process or the ethanol yield, and combustion process, and how much amount of ethanol you will get from the ethanol fermentation process. So here you have a question. It states that the theoretical ethanol yield that you have from a C6 sugar, so carbon 6, so 6 carbons are present in that sugar form, is 700 kg per ton. They are asking you to calculate the approximate concentration of sugar present in the biomass if the theoretical ethanol yield constant is 0.51. So this is a very simple question. I hope you will be able to answer this question. Let's just solve this question. So your theoretical ethanol yield, what is it? It is nothing but it is your concentration of sugar in that biomass times your yield constant. So your entire sugar will not be able to get converted to ethanol, right? There will be certain fraction. If you see in case of this chemical conversion also, when we saw, if you see some amount of the sugar, that is your glucose sugar, will get converted to carbon dioxide. So it's not that all the amount of sugar that is present in your biomass will be converted to ethanol. So there will be a certain percentage of that sugar content which will be released out as gas, carbon dioxide gas. So that is the reason we are supposed to calculate the theoretical ethanol yield. So this is very simple here. So you have the concentration of sugar in the biogas. So that will be 700 kg per ton, and your yield constant value is given, that is 0.51. So that's all simple. So your theoretical ethanol yield will be nothing but 700 times 0.51, it will be approximately some 350, around 350. 357. And since it's a constant, it is a dimensionless this thing, that yield constant, so it is kg per ton. So what it actually means, so for every ton of biomass, for every 1 ton of biomass, you have 700 kg of sugar, and then when you process that sugar, you get 357 kg of ethanol. So ton is nothing but 1000 kgs. So for every 1000 kg of the biomass that you are going to subject for the fermentation process, you will be getting the sugar that is present in the biomass will be 700 kgs, and for every 700 kg of your sugar that is going to undergo the the fermentation process, you will be able to obtain 357 kg of ethanol. So let's just write that for 1000 kg of biomass, you have 700 kg of sugar, and this 700 kg of sugar, this is something that is fixed, like in the sense this much amount of the sugar will only be present, or this much amount of the sugar only you will be able to get from this much amount of biomass, right? So for this much amount of the sugar that I have, I will be able to get 357 kg of ethanol, and this is theoretical. Similarly, we have another question, same type. Here they are asking us to calculate again the theoretical ethanol yield, and then they have given us the concentration of sugar as 350 kg per ton, but in two different units. One is in kg per ton and another one is in liter per ton. So the theoretical ethanol yield will be I hope it's visible. Concentration of your sugar in biomass is 350 kg per ton, and your yield constant value is 0.51. So this will be approximately, I guess, it will be around 175. It's just half of that, so 178.5 kg per ton of theoretical ethanol yield. Theoretical ethanol. So this is the theoretical ethanol that you yield that you will get, 178.5 kg of ethanol for 1 ton of biomass. Now you are supposed to calculate it in liter per ton. So that is nothing but, if you divide this by density, you will be able to get the theoretical ethanol yield in liter per ton units. So that is nothing but 178.5 kg per your density is given as 0.789 gram per centimeter square cube. So here it is in kgs and here it is in grams, so you are supposed to convert this into kg per liter, right? So 1 centimeter cube is nothing but, I hope you will be knowing this, 1 ml, or you can recollect this also. 1 centimeter cube is nothing but 1 ml. So 0.789 gram per centimeter cube is nothing but, it's equal to, you can calculate. So 1 gram is nothing but 10 power minus 3 kgs, and 1 ml is nothing but 10 power minus 3 ml. So both that will get cancelled, so you will be getting 0.789 kg per liter. Now you just need to divide this. So what will be the answer? One 178.5 divided by 0.789, 226.235 liter per ton, because that kg and kg will get cancelled out. So this is the theoretical ethanol yield in terms of both kg per ton units and liter per ton units. So let's go to the next question. I hope this one was a very simple question. Here you know the concentration of sugar that is present in your biomass, and since all your sugar cannot be processed to get ethanol, so all your sugar cannot be processed towards ethanol, because some amount of it will be generated out as carbon dioxide and other gases. So you multiply that with your yield constant, that is yield constant, and then you will be able to get your theoretical ethanol yield, both in terms of kg per ton and liter per ton. Now we move towards the next question. So here let me give you some time to see the question or read the question. So here we are asked to develop an equation for the combustion of propane with theoretical air and 30% of excess air, and then they are asking us to calculate the operating air to fuel ratio, that is A by F ratio of this system. So I have given this question, this is the question, and the respective equations are there. So propane, I hope everybody knows the formula. Propane is nothing but, propane is 3 carbon, 3 carbon atom hydrocarbon. So in that hydrocarbon, in the propane hydrocarbon, 3 carbon atoms are there. So C3H8. This is propane. Now this is going to be subjected to combustion process. So C3H8 is going to be burnt in the presence of air. So air usually it consists of nitrogen is the major constant. Apart from that, you have oxygen, carbon dioxide, moisture, and other different type of gases that are present. But the major two gases that is present in your air is your nitrogen and oxygen. Since the rest part is is very little, the fraction is very small, so we usually neglect that. So if you say air is going to combust my material, I will take up only with the oxygen and nitrogen. This is going to react, and then I am going to, at the end, since it is we are using theoretical air and also excess of air, so I will be getting carbon dioxide only. If you do an incomplete combustion, then you can get carbon monoxide, CO also, and you will get water. And if you see here, I have written this 3.76 you know times n of nitrogen on both the side of the reaction. The reason why this is written is because the nitrogen does not take part in the combustion process. The nitrogen is inert, it does not react with any other component to form products. So the nitrogen will remain in the air, but it will not undergo any kind of combustion process. It is inert, it will not react, and then with the product it will be, what do you say, it will come out with the product. So the nitrogen, the amount of nitrogen will remain same in both the reactant side as well as the product side. So this will be the equation if you are using exact quantity of air, like you don't have any excess of air that you will be using for the system. So if you have excess of air, then again you need to then after combustion, whatever that amount excess is present, or the amount that that does not get used up for the combustion process, will come out with the products, right? So you are supposed to add that also if it is if you are supplying air in excess. So let me just write that. This will be in exact quantity of air, and this will be in excess. And if you see, the reason why we add 3.769 is because for every 1 mole of oxygen that you take in the air, you will have 3.769. See, because the air is having, or air is composed of 79% of nitrogen and 21% of oxygen, right? Oxygen gas, nitrogen gas and oxygen gas. So since here we for our purpose here we are taking the contribution from the rest of the gas as negligible, so we take it 79% of nitrogen and 21% of oxygen. So for one, so if you divide the 79 by 21, then you will get 3.76. Let me show that. 3.76. So what it means is, for one in air, for every 1 mole of O2 or oxygen gas, you will be having 3.76 moles of nitrogen gas. So that is what is the meaning. So here we are supposed to complete this equation. So if you see, this is just a skeletal equation, it is not a balanced one. So first let us do the balancing for this exact quantity of air equation. So you can write this as N 3.76. So here if you see, in the left hand side, the reactant side, you have 3 carbons, and this is the only product which have carbon in it. So here it should be the coefficient for CO2 should be 3. And if you see hydrogen also, only in case of this propane you have hydrogen, and you have 8 hydrogen, and in the reactant side only water molecule is present, and it is having H2, so 4. So that if you see, for both carbon and hydrogen, the number of atoms in the reactant side and the product side will be balanced. Now you have only your oxygen and nitrogen. So if you see oxygen in the product side, totally you have 6 from here, and from water you have 4. So 6 plus 4 is 10. And in the reactant side, oxygen, if you see, it will be 5 because it's O2, right? So 10 atoms. So here 10 atoms, and in the product side 10 atoms. So this is balanced. So now you are just supposed to balance the nitrogen, and as I said, nitrogen will not participate in any of the reaction. You are just supposed to mention what is the like it just comes out. So how many moles will come out of the in the product side would be 5 into 3.76. That will be the coefficient for your nitrogen gas that will be coming out of your system. So 5 times of 3.76, 18.8. I hope you are able to understand this a very elementary level equation balancing. So now we have our equation balanced, right? So we are supposed to calculate the operating air to fuel ratio. So since we assume only theoretical amount of air is being used, so what is what it will be? This will be nothing but mass of air times mass of fuel, and that will be nothing but 4.76 times n is nothing but your 5 here, times molecular weight of air times molecular weight of your fuel. So we are supposed to calculate the molecular weight of air and molecular weight of fuel. So fuel for us, it is propane. So molecular weight of propane is, carbon is 12, so 12 times 3 plus 8 times 1, hydrogen mass is 1, atomic mass is 1, and atomic mass of carbon is 12. So that will be 36 plus 8, so 44 gram per mole. So for 1 mole the weight, so for so 44 grams of propane is present in 1 mole. Now we have to take molecular weight of air. So since air is a composition, as you see, of both oxygen and nitrogen, you have to consider both the fractions here when you are calculating the molecular weight of air. So 79% is nitrogen, so 0.79 comes from nitrogen, and N2 gas, nitrogen gas, and molecular weight is 28, and 21 parts or 21% comes from oxygen. So oxygen's molecular weight is 32. So if you calculate, you will be getting 28.84 gram per mole. You can also try calculating here. 6.72, 22.12, 28.84 gram per mole. So here you need to calculate the average molecular weight by considering the composition of both nitrogen as well as oxygen. So after this, it's just substituting. So you have 4.76 times 5, and you have your molecular weight of air as 28.84, and your molecular weight of fuel is 44. So its value will be 4.76 times 5 times 28.84, the whole divided by 44. So it will be 15.5, 5998 kg of air per kg of fuel. So if you see, the amount of air that is going to be present compared to the amount of fuel is more. So for every 1 kg of fuel, you have 15.5 kg of air. So this means this is a fuel lean mixture. And then so now we are done with the exact quantity of air. We are supposed to calculate what happens if we have 30% of the excess air. So when I say 30 percentage of excess air, what it actually means is I am supplying stoichiometric quantity of air. On top of that, I am going to add 30 percentage more. So that will be, let us do that. So what is the theoretical quantity? It will be this 5 times O2 plus 3.76 times of the nitrogen gas. This is nothing but it is my theoretical air. To this I am going to add 30 percentage. So 30 percentage of this will be this. This will be added on top of the theoretical air. So which will be nothing but this two together, right? Because it's in excess, you are adding it in excess. It's not that only 30 percentage you are supplying, but you are adding 30 percentages in excess. So this means 1 plus 30 by 100 is 0.3 times this one. One 1.3 times of the theoretical air requirement. So now you know how much amount of the air you have to supply for the combustion of your propane. So which means, let's take up with this equation, and as I said, the nitrogen is inert, so it will come out of the product side, and the excess of the air that you supply, which is not getting involved in the combustion process, will also come out of your system. So it will be 1.3 times of 5. So now you know what will be your air requirement. You just need to balance the equation. Again, you need to balance atom by atom. If you see for carbon, here it is 3 and only carbon atom is present in carbon dioxide, so 3, and here 8 atoms of hydrogen, so 4, and the total oxygen here will be 1.3 times 5, so that will be 6.5 in the reactant side, and 6.5 times 2, so 13 in reactant side and 10 in product side, so it will be 1.5 here, and then the rest will be just balancing the nitrogen, that is 1.3 times 5 times 3.76. That will be 16.92. Just it's 1.3 times 5 times 3.76, 24.4. So this will be our balanced equation. Now for this we are supposed to calculate the A by F ratio. That is again nothing but 4.76 times of N. N is nothing but the total moles of the air that is actually involved in the combustion process. So here, since 5 moles of the air is participating in your combustion process, we multiplied it into 5. Here we are supposed to multiply that with 6.5, because 1.3 times 5, right? This into molecular weight of air is 28.84 divided by molecular weight of fuel, that is propane, 44. So if you multiply, then you will be getting 4.76 times 28.84 times 6.5, the whole divided by 44, 20.279. kg of air per kg of fuel. And if suppose we are asked to calculate what will be the volume of the carbon dioxide or any of the element, then it is nothing but it's the moles of that particular element to that of the entire moles in the product side. Suppose if they ask, like in the next question, if you see, they have asked the volume of CO2 produced. So 3 moles is actually produced, 3 moles of carbon dioxide is produced. So 3 by the total number of moles in the reactant side. So it will be 3 plus 4 plus 24.44 plus 1.5. (32.94). So 3 divided by 32.94 will be 0.091. This will be the fraction of carbon dioxide that will be produced in the combustion process. So we have one more question, but we are actually running short of time. So this question, either you can take it as an home task or homework or an assignment, or probably we will discuss this in the next class. So in case if you have any doubts, then please let me know now, or we can conclude our session. Let me just stop presenting. So if you have any doubts, then please let me know, or if you have any feedback also, then please let me know before we conclude our session. So if you don't have any doubts, then let's just conclude our session for today. I thank you all for joining the week 9 live interaction session this afternoon on 24th March from 5 p.m. to 7 p.m. Our week 10 live interaction session will be on 31st March, same time 5 p.m. to 7 p.m. I thank Professor Vaibhav Vishant Gaud sir, Professor Ananda Lakshmi ma'am, as well as the NPTEL team for providing me with this opportunity to interact with you all in this Sunday afternoon from 5 p.m. to 7 p.m. So let's meet next week. And till then, in case if you have any doubt, my email ID is always available. You are always welcome to email me at any time. I will respond to it as soon as possible. So thank you and have a happy weekend. Bye.